Hey again, everybody. In this video, I'm going to explain what the P-series is all about. And this is actually pretty useful little shortcut, if you will, because it kind of relates to what we did with the integral test, but it also gives us a little bit of a sort of a trick. So the P-series basically looks like this. It's clearly a series. 1 over n to the P. Okay? So it's when you have 1 over n to some power. And we've already explored 1 over n, that's the harmonic, we already know diverges. We've already explored 1 over n squared, which converged, which we showed with our integral test. And now it's just a matter of what about all other values of p. Okay, maybe we can find some kind of pattern here. So is it safe to say that we already know that p cannot equal 1? Okay, if p equaled 1, we go to the harmonic and we're done. It's an easy explanation. We've already explained it in 2 different ways. So we really just need to explore, well, you know, yeah, okay, when p is 2 it works, but does it work for all values greater than 1? Does it only work for 2? Does it work for values greater than 2 or greater than equal to 2? What about less than 1? So we want to kind of see, does this, okay, so this one obviously diverges. We want to see what happens when p is greater than 1 or p is less than 1. So let's approach this the same way we did when p was 2 and actually do our integral test. So if I make this into an integral, 1 over x to the p, and I do my improper technique, improper integral technique. It sounds terrible when I say it. We're going to go from 1 to t. This is, let me rewrite it as x to the negative p. Maybe that'll help. Because I do want to take the antiderivative of this. Again, since p is not 1, we've already ruled that out. I don't have to worry about natural log. Simply because if I did that, I would get divergent again, which I've already proven. So I'm not going to do it again. So the limit as t goes to infinity, this is going to be x to the negative p plus 1 over negative p plus 1, evaluated from 1 to t. So this is just doing my reverse power rule. When this was negative 2, we had x to the negative 2 plus 1 over negative 2 plus 1. Okay, we're just generalizing. Let me write that a little bit easier to follow. X to the 1 minus p over 1 minus p from 1 to t. Alright, so that's going to be t to the 1 minus p over 1 minus p minus, if I put a 1, that's just 1. If I put a 1, I'm sorry, a 1 here. 1 to the 1 minus p is just 1 over 1 minus p. Okay, and as t goes to infinity, okay, I have a t in the numerator going to infinity. So again, at first glance, you're like, oh geez, this is just going to go off to infinity. Dividing by 1 minus p does absolutely nothing for me. Minus 1 over 1 minus p does absolutely nothing for me. Those are just numbers. So I'm really just focusing in my attention on the t to the 1 minus p. If the t to the 1 minus p, or I should even, actually let me even focus just even on the 1 minus p. If the 1 minus p is greater than 0, if I'm positive, right, then my t is going to go off to infinity. Well, when is 1 minus p positive? Well, when 1 is greater than p, aka p less than 1. So if p is less than 1, this integral diverges. Think about it. If p is less than 1, let's just pick like negative 10. If p is negative 10, then this is going to be t to the 1 minus negative 10, which is t to the 11th. Okay? That's just going to go off to infinity as t goes to infinity. So if p is a negative, not a negative number, if p is actually less than 1, okay? If p is less than 1, then this is going to go off to infinity. If I go the other way, if I want 1 minus p to be less than 0, right? If I make my exponent negative, well then that t gets down into the denominator. That's where I want it if I'm trying to show convergence. So I need my 1 minus p to be less than 0, which means I need 1 to be less than p, aka I need p to be greater than 1. That's the same thing. And there we go. So a p-series will converge as long as the p-value is greater than 1. If it's less than or equal to 1, it will diverge. Okay? Let me just explain again. If you've got it, you can probably move on. If not, just listen one more time. This is the only part that's giving me trouble with the t going to infinity. That's the only part that has t in it. Okay? So if this t to the positive power is going off to infinity, then this whole thing is undefined. Okay? It's infinite. It's unbounded. if this t is raised to a power that's a negative power, well then now my t is going to be in the denominator, and the fact that the exponent's going to infinity in the denominator is simply going to make this part go to 0, so then my actual limit will exist. It will be some number 1 over 1 minus p. Okay, it might be positive or negative, I don't know for sure. Depends on what p is. Okay, so if my exponent is positive, this actually diverges, and that's here. If this exponent is negative, then my t goes to the bottom, and my limit will reach a value, which means my integral converges. Okay, and that's what happens here. So my p series will converge when p is greater than 1. Okay? And obviously the p series will diverge when p is less than or equal to 1. Again, if it equaled 1, we have our harmonic, so that's like a no-brainer. But even if it was, negative 2, if I had 1 over n to the negative 2, think about what that would be. That would actually make this n to the positive 2, right? N to the positive 2. And n squared, it would be like x squared, and x squared, of course, is not going to converge to anything. Okay, so it kind of does make sense if you think about it that way. Okay, so there's your p series. Let's do an example or two. Let's see. Actually, very simply, how about 1 over x to the 7th? Oh, I should do n to the 7th, sorry. N to the 7th. Integral test? No, thank you. I think I'll just do a p-series test and just say this is a p-series with p greater than p equaling 7, which is greater than 1. Oh god, that was terrible. That was terrible. Let's try that again. P-series. Once I learn how to edit these videos, this will look a lot better. With p equaling 7, it's just that my 7 looks like a greater than, and that's what threw me off. 7. 7. 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 7. Okay? So p equals 7, which is greater than 1. Therefore, this series converges because of the p-series. That's it. That's all you actually have to do. Well, you don't actually have to do all this stuff. That's just me being an idiot. But the idea is you can simply recognize this as a p-series kind of problem, and you can use this as an actual justification. Okay? All right. Let's try one like a homework style problem and see if you can do it. Okay. Let's see. What's a good one? Ooh, this is a good one. Here's a good homework problem. This is a good like warm-up kind of problem. Can you do this one? All right. You guys try it first. Okay, pause the video, give it a shot, see if you can get it, and then come back and I'll do it for you. All right, here we go. At first glance, I do not understand how this could possibly be a p-series problem. Okay? Because you see all sorts of stuff mixed together. But if we just rearrange it, it's not so bad. This is going to be 5 over n cubed minus 2 radical n over n cubed. And we can simplify that even further. This 5 is just a 5. I can pull that 5 out. Wow, look at that sigma. Look at that sigma. I am so proud of myself right now. Look at that. Look at the evolution of my sigma. Amazing. All right. So I've got 1 over n cubed here. Minus, I can pull out a 2 here. And let's see, square root of n over n cubed. So that's n to the 1/2. This is n to the 3. So this would be 1 over n to the, what's that, 5 halves? Did I do that right? 3 minus a half, right? 2 1/2. And this and this separately are both p-series. So this series will converges of p-series, or because it's a p-series, with p equaling 3, which is greater than 1, and this one converges p-series, p equaling 5 halves, which is greater than 1. Therefore, this series converges. Okay, it's actually that simple. So hopefully, you can recognize a p-series when it's there. And I mean, I'm looking at that. I'm like, okay, good luck taking that integral, right? You really need to split it up so that you can actually do it. And we could do these integrals, right? But if you can see this, if you can see the separation, well, then there's really no reason you can't see the p-series kind of hiding in there too. Okay, let's try one more. I know this video is going kind of long, but the p-series is kind of important, so I'll just piece it all together for you. Okay, let's try one that you kind of have to do a little bit of detective work. So how about this one? How about if they give it to you like this? Okay, what if they give it to you in that form? So you're looking at that, you're instantly thinking series, of course. The question is, are you immediately thinking geometric? Which isn't a bad thought until you look, for a couple seconds and say, okay, to get from 1 to 1/8, obviously I have to multiply by 1/8. But to go from 1/8 to 1/27, I am not multiplying by 1/8. Okay, maybe you see from this one to here you can do it, but you still have to deal with every term. That ratio should be common throughout the entire series. So we have to come up with our own formula for this one. And luckily it's not actually that bad. Okay? So you look at it and you say, alright, well that doesn't really help me. 1/8. 8 is also, these are, I don't know if you recognize these, but these are actually perfect cubes. Okay? So I have 1 obviously over something. 1/2 cubed. Okay, 1/3 cubed. Ah, there we go. So that must have been 1/1 cubed, which means this is 1/n cubed. Okay? So 1/n cubed. 1/1 cubed, 1/2 cubed, 1/3 cubed, 1/4 cubed, etc., etc. And then I think, actually this is one of the examples I did earlier, converges, p-series, p equals 3, which is greater than 1. Thank you very much. Have a nice day. Talk to you guys later. Bye-bye.